In the last video, I've talked about how if you have a current going through a long straight wire, how the magnetic field that would appear around this current would be in the shape of circular loops centered at the wire, right? And you have starting with small loops, then you get bigger loops, and the magnetic field gets weaker and weaker as you go further and further out. And you would have this pattern all along the wire where there is current. But this pattern, as I emphasized, is only correct when you are quite close to the wire, when the distance from the wire is quite small compared to the length of the wire. When you're very close to the edge of the wire, the shape of the pattern probably would most likely change. Now, what I'd like to talk about now is the connection between the magnetic field pattern around the long straight wire and the magnetic field in a solenoid with lots of turns in a long straight coil. Now, in both cases, if you think about it, in both cases, we are talking about the same wire. Right? This is a long piece of copper wire, for example, that has been stretched in a straight line. That might be actually the same piece of wire which I've bent round and round to make it into a solenoid. So it's the same wire and same current, but just bent into different shape. So surely there must be some connection between the magnetic field around this wire when it is straight, and around the same wire when it's bent around. So why is it that the magnetic field pattern looks so different? Let's take a look at this in a bit more detail. Okay, so let me clear up some space for drawing. Now, let me just focus on start with this single long straight wire. Now, instead of taking the jump from a long straight wire to lots of turns in a long solenoid, what I'm going to do is I'm going to take this long straight wire. Okay, I'm going to do something simpler first. I'm going to just bend this long straight wire around into a flat circular coil. Just a single circle, not lots of turns like that, just a single turn. Okay, so I'm just going to bend it around, and it's still connected to a battery that gives it the current. Okay, so there's still a battery, there's still a current. Right, so there is this current going through here. Now, we might imagine that when you're quite close to this current, let's say if I just really focus on, say, just this short bit down here, and if I'm very close to it, this bit would look just like a straight wire, right? If I just look at this bit very closely. So if I'm very close to this short section of the wire, for example, I would expect that the magnetic field around this short section of the wire should not look so different from the field around a long straight wire. So when I'm very close to this, I would expect that the magnetic field would just be circles, right? Just circular loops around it. just like this. Okay, so I think that is reasonable to expect. And in fact, if I use my right hand thumb rule, if you remember what that is, just put the thumb, point the thumb of your right hand, put your right hand close to the, just stretch it out flat, put it close to the wire with your thumb pointing in the direction of the current, and then wrap your four fingers around the wire, and the fingers would point in the direction of this magnetic field. So we can apply to this short section of wire down here. Just put your right hand flat against this wire, but with your thumb pointing in the direction of the current. Then when you wrap your finger around the wire, you'll find that the magnetic field would go around in this direction. Okay, so let's repeat this idea for another point along the wire. Let's say here, when we're here, the current is going in this direction. So if I'm quite close to this part of the wire, this part would look roughly like a straight wire to me if I'm very close to it. So I would expect that close to this part of the wire, I would also get circular loops or magnetic field around it. Okay, and using my right hand thumb rule again, I would find that the magnetic field would point in these directions around here. And I can just keep doing it. I can do it here as well. So around here, the magnetic field pattern should be just circular loops. Okay, and the directions should be this way. And that would be correct, right? These are the correct patterns around close to the wire in this flat circular coil. But of course, if you move further away from the wire, the pattern would start to look different from this regular, this concentric circles. And what it would look when you're around the middle would be this. If you're right in the middle, actually, it would be a straight line. It would be a straight line. And if you are a bit away from the center, it would look like this. Okay, and if you're a bit further away, it would look like this. So you can expect that it's sort of, if you move further out from the center, as you get closer to the wire itself, it sort of looks more and more like these concentric circles. Okay, so at first it's quite straight and a little bit bent, and it looks more circular, and then it looks quite circular as you go close to the wire itself. So overall, the overall pattern would actually look like this. Okay, and as to the direction, we can sort of see how the direction carries over from these little circular loops to the few lines nearer the center. If you follow the direction of these circles, these circular lines, you see that it sort of goes this way, and therefore direction of this one should be this way, and this line should be that way, that line should be this way, this line should be this way, that line should be this way, and then this is this way, and so on. So it makes sense, right? They agree, right? The directions agree all around. And this is what it look like. There's one more thing that I should mention about the direction. The way I've described of getting the directions of these magnetic field lines around the center of this coil, it's a bit tedious, right? You have to look at the circular rings close to the wire, and then you sort of slowly move towards the center and checking the directions all the time. Now that's a bit that's a rather tedious way to determine the directions of this field near the center of the circular coil. There is actually a quicker way. And the way is similar to the way we would use for solenoid, and that is again using your right hand. It is still a right hand thumb rule, right? Now, but in this case, instead of having our fingers wrapped around the directions of the magnetic field, this time stretch out your right hand and wrap your fingers around the direction of the current instead of the field. And if you find that you can wrap your four fingers around the direction of the current, then your thumb would point in the direction of the magnetic field, just like you would do it for a solenoid. So now that we have a better idea what the magnetic field around a single turn of wire look like, imagine putting lots and lots of these turns side by side. Then you would just get the solenoid. Right? A solenoid is nothing but lots and lots of little turns of wire. So each of these turn of wire in a solenoid is just a circular coil. So let me try and see how this can actually turn into this. So let me start by taking this loop and drawing it here. Let's say I have a loop there. Now if I have and let's say I have another loop there. I should draw it bigger. A loop here, a loop here, a loop here. I'll just draw 3 loops. Okay. Let me just not draw them close so that I can join them up later. So one loop, another loop, and another loop. Please bear with me. So these are meant to be connected in some way so that the currents can flow through it. And suppose that I'm trying to imagine that these 3 loops are those 3 loops, and then I have this current going through it that would go round and round so as to produce this field pattern. So let's say I have a current going around this way. Now it's a bit hard to think of this in 3D, but think of this arrow here that I draw as being closer to you, and that other side is being further away from you. So perhaps I should draw this part a little bit thicker. That's not good. Let me try and draw this part thicker. So this part is a little bit thicker, and it's supposed to mean that this part is closer to you. That this is meant to be a 3-dimensional drawing. Okay, right. So this part is closer to you, that part is further away. Okay. Now, what about the direction of the magnetic field then? Let's take over this idea and see what we can do here. So around each loop, we would expect that there would be this little circular magnetic field that go this way. This one going in this direction, going around in this direction. Okay, so it's the same around all of this. Magnetic field going this way, this way, this way, this way. Same on the other side as well. So sort of magnetic field going around this way, this direction, going around in this direction. Okay, and around the center of the loop, it would look more like that. So I would have this straight, right at the center would be a straight field line from here, and then a bit further away you will have slightly bent field lines coming out from there. Okay, that, and likewise for this. So a straight field line from there, a bent field line from there, a bent field line from there. So they all look the same. So you can imagine that that's what the magnetic field, or at least that's the kind of magnetic field pattern that each of these loops would produce. Okay, so if you imagine that, say that's loop number 1, that's loop number 2, that's loop number 3, and so on. So that would be my loop number 1, number 2, and number 3. Okay, what happens if I put all these close together, like I do in a solenoid? Then you can imagine that these field lines, they will all merge into one another. Okay, so this and these curved lines, okay, those further from the center, if you have just a single turn of coil on its own, this will be a curved line. But if you put lots of these turns very close together, these curved lines actually merge into a straight line. Right? These curved lines would actually merge into a straight line. So that's how we get these lots and lots of straight lines in a solenoid. And because of this, when you're in a solenoid with lots of turns very close together, the field is actually uniform. The field is actually uniform. Now, if you are in a single turn, if you just have a single turn, the field at the center would actually be different from the field away from the center. Away from the center, it would change. Okay, but when you put lots of these loops together, the field is actually very uniform. It's actually very uniform over the area, over say the area of any cross section in the solenoid. It's only when you start coming out the solenoid that the field starts to become weaker as it spreads out. So in this way, we can understand how the magnetic field in a solenoid that you would use for an electromagnet, how these are formed, how this field is formed from the individual field patterns of the single turns of the single coil, like this, and how this single coil, this circular coil, how its field pattern is in turn formed by the combinations of lots and lots of circular loops that would come from a long straight wire.